Will you erase that?
Okay. So, have a seat. Alright, so I'm kind of just going to sit here and talk about all. Is that cool? Sit here and talk about all the.
Laziness is a sin.
Can I get this? Alright. Okay, first and foremost, obviously we've been talking about waves without really defining a wave. A wave is a motion of a disturbance. It's the movement as a result of a disturbance. And I'll explain what I mean. Because a wave does not move the medium that it is in. So when a wave travels through water, the particles of the water aren't moving with the wave. I mean, it's going up and down, but it's not traveling horizontally with it. When a wave in water, like on the beach, comes, the water at that given point is not moving with it. It's just disturbing the matter. The matter's just going up and down. I know it's kind of weird to think about.
Is that true for sound? I thought sound was pressure though. So like, wouldn't it be like?
Sound doesn't travel on a medium. It's right
No, sound needs a
No,
medium.
sound does is light.
Okay, so let me explain. So a medium is a physical environment through which a disturbance can travel. For example, water is the medium for ripple waves in a pond. Okay, if you were to cause a vibration on water, the wave would pass through that medium. I know it's kind of hard to think about, but the water doesn't get carried with it. Okay, that's weird. I know, it's weird to think about.
Then why do you get carried with a wave?
Because
You're just a big old particle.
yeah, but what happens is that particular wave hits you, transfers energy to you, which causes you to move.
So the energy.
I see.
Yes, and so obviously a wave is going to get less strong after it hits you. Okay, and we'll talk about how strength of waves work today as well. Okay? Waves that require a medium through which to travel are called mechanical waves. Examples of this would be, waves traveling through water, sound waves. I don't know if you've ever heard this, but you cannot hear things in outer space. Why?
There's no medium out there.
There's no medium through which vibrations can travel through. So if I took a cell phone, put it in a vacuum, and you called it, we couldn't hear it.
Because you have silence less strong.
So light waves are
Okay? So, now listen, I know it's difficult, but a lot of waves need a medium through which they disturb through, if you will.
What's a wave that doesn't need
Light. Oh! Light is a wave, but it doesn't need a medium to travel through. That's why it can go through outer space and not worry about having to have a medium. And the difference is sound waves and water waves are caused by a vibration. That's not the case for light. Light is actually, we'll get to this when we talk about light, but what propels light through things has nothing to do with the vibration, it has everything to do with an oscillating electric and magnetic field.
Isn't light like a wave of something else in a particle? Or
Oh yeah, well, yeah, that's a whole another ball.
Sort of both the
Particle physics, yeah.
Yeah, but what's the other thing?
Oh,
Stored it when it goes through
Wave particle goes to water.
It bends, it doesn't, it bends. Okay. Alright, anyways, so a lot of the rest of the stuff should be, well, not this. Okay, so this isn't overly difficult, although you do need to know it. When you just have a single pulse, that's a pulse wave. So just imagine having a slinky and giving it one vibration. The pulse would go through it and you wouldn't have multiple repeated waves. You would just have one pulse. Okay? Stop! Okay? It's not overly complicated. Now listen, when you have a source that is repeated, a vibration source that is repeated, you get your periodic wave, which is going to be basically a bunch of pulse waves repeated. Okay? A wave whose source vibrates in simple harmonic motion is called a sine wave, hence what I put on the board earlier today that you guys dealt with. Okay? Now, okay? Now, this obviously is not a pulse wave, is it? It's a periodic wave. Okay? Because you have continual repeated vibrations of an object. In this case, there's a vibrating blade. Okay? As a sine wave created by this vibrating blade travels to the right, a single point in the string vibrates up and down in simple harmonic motion. What that simply means is, in this situation, you have the wave that's progressing to the right, but no part in the rope moves to the right or left. So really what just happens is this just goes up and down right here. So that's what I mean when I say waves don't transfer matter, they just transfer a disturbance.
What's the difference between this and a sine wave?
Well, since this is simple harmonic motion, this is also a sine wave too.
Oh,
It's in the medium.
Okay? I know it's hard to think about, but when a wave comes through water, the water is just going like this in place, and it's the disturbance that's going through it. Yes.
Real talk. Real talk disturbances. Stop.
All right. So there are two types of waves that we will talk about. Okay, this may be where it gets a little bit conceptual, that we have to focus a little bit. Okay, transverse wave is a wave whose particles vibrate. I want to make a note that this is specifically important. So a transverse wave is a wave whose particles vibrate perpendicularly. Okay? What that simply means is your particles are going up and down, but your disturbance is going perpendicular from it. Okay? The particle itself, the matter itself, just going up and down. The wave, though, is progressing, or the disturbance is progressing perpendicular to that. Okay? And we've already defined crest, we've already defined trough. We know what a wavelength is, so I don't need to say anything more about that. No.
when is there not going to be a wave like that?
I'll show you.
Oh,
Grimes, that was the coolest thing you've ever said.
I'll show you. The other type of wave. Is a longitudinal wave. So transverse wave is where the particle is moving perpendicular to the wave. A longitudinal wave is when they're going parallel to each other. And that would be an example of a spring. So the wave or the disturbance would be going that direction, correct?
that's like when you push the slinky and it like slinks together.
Yeah. So like the difference would be like going like this with the slinky versus, yeah, pushing a slinky. Okay? So a longitudinal wave, the key word here is parallel. Okay? The motion of the wave is going this way, but the particles are vibrating and going like this instead of like this. Okay? Now, here's a couple vocabulary words that are a little bit new, okay, but they represent very similar things. When you're talking about a spring situation, they have something what's called high density and high pressure. What that is referring to is the compressed region of a spring. The high density region represents the peak or the crest. Everybody see this and this are the same wave, just this is sine form. So do you see how the two compressed regions of the spring are representing the two crests on a sine wave? Okay, so high density is referring to compressed. It's really dense, it's compressed. Okay? Low density is where you're at your most stretched, and that's always going to be what you would consider your trough. And you can see there are 2 stretched locations and 2 troughs that relate to the same point on the graph.
This is how sound works, right?
What was that?
This is longitudinal wave is a sound wave. Is that how sound works? Or is sound?
Yes. Yep. Yep.
How do we know that?
You'd have to know. Just think of like a tuning fork. So a tuning fork like vibrates back and forth, and so it actually pushes air, and then which pushes more air, and it's just like a big. You'll see it when we get to vibrates. So like when you vibrate your lip, what you're doing is just creating a high region, low region, high region, low region of air molecules. Okay. You'll see it when we get to it. Yes, what you're doing is you're compressing air, which then creates a region of low density, which then creates a high region, then a low region.
What's that air?
Okay. I think just asked a question or made a statement which is coming in the future, and I just tried to kind of explain it without any background information.
That isn't gonna be Tuesday, is it?
I don't know. Okay, so I don't know if I really need to talk much about this either. We already know what the frequency of a wave is, yes? We already know what the period of a wave is, yes? And we know that they're inversely related to each other, yes? Right? We know what frequency is, we know what period is, and we know that they're inversely related.
Oh yeah, it's 1 over.
Yeah? Alright, we're ready to get out of class. 7 minutes.
Sounds like lunch yet.
Okay, this is where it's a little bit new, but not if you took advanced chem. It looks a little bit different than the formula we use in advanced chem. Do you know? I'm curious if you two can remember what what was different about this equation in advanced chem. No, F was the same.
Wavelength wasn't
It
wavelength.
wasn't that. It was what?
Particle speed.
It was C.
Oh yeah.
Good old. The speed of light.
Because C represents the speed of light.
C equals F of wishbone.
Okay? Now,
Good old wishbone.
what's important to know here is this is why light travels at a constant speed. Okay? So the wavelength is related. So I know we said frequency and period are related, but so are frequency and wavelength. If you have let me kind of explain what I mean. Oh, we have a wave like that, and then we have a wave like that. Which one has a high frequency? Has a high F, but then it also then has a low what? Wavelength.
Low wishbone.
And it does have a low period.
That's a
too.
lambda, but
Wait.
I put half-life.
Okay, because frequency or wavelength is from here to here, right?
Yep.
Amen. Okay. Here, up here, it has a much lower frequency, but a
higher
higher wavelength.
Bigger.
because it's longer.
Okay. Make sense? So they're also inversely related. Okay.
So does that mean a heartbeat stops the wave? You make a graphical wave, or is that?
That's a go.
I don't think so. So it's not like a sine wave.
So it's not saying people
I don't
It's just
know,
saying
to be honest.
people don't die. They just
I'm singing.
Okay. I think this might be the last slide. Well, technically there's a math problem, but it's using the wave equation, which is like just two variables multiplied by each other.
You can't divide.
Okay, so
It's actual
I
law.
can't divide.
waves transfer energy by the vibrations of matter. So really what that disturbance is essentially just a transfer of energy from a vibrating source through a medium. Okay? So some vibrating source caused a wave in water. What that wave is really just an amount of energy. Does Does that ring
see.
turn on the light bulb in any of you guys' brains?
That light, incandescent light bulb is what it's supposed to.
No, it's just moving through the wave. Okay, now this is why if a wave like comes across and comes into contact with something, the wave loses some of its power because it's being dissipated when it hits some source. And I can this should make sense. It says the rate at which wave transfers energy depends on the amplitude. What would you be more afraid of? A small wave in the ocean or a big wave in the ocean? A big one, right? Okay? The big wave in the ocean has a big amplitude or has a greater distance from equilibrium. Would you agree with that? Yeah. Okay? The amplitude tells you how much energy the wave has. The bigger the amplitude, the more energy is being transferred by that wave. And therefore, the reason why you get carried more or it hurts more when you get hit by a wave in the ocean.
Are waves in the ocean actually the same thing as these waves?
Yes, absolutely.
It's a water wave.
So there's wave.
Gravity is the force, I guess that makes sense.
I'm not sure what the vibrating source of a wave is.
The Earth's crust.
I don't know what the vibrating source of a wave is, but it definitely is a wave that's transferring energy, just like a typical wave is. Okay? Now, I said this already, but the greater the amplitude, the more energy that's being carried. Okay, for mechanical waves, energy is transferred proportional to the square of the amplitude. And one thing that's really important is when the wave, over time, the wave will die down. Why?
Because of the Murphy's law.
Entropy.
It's not a 100% efficient, because you're going to lose energy over time due to friction and other air resistance, due to all sorts of stuff. However, waves do a very good job of transferring energy efficiently. Very good job. Part of the reasons why. Oh, good question.
But the second law.
I'm not 100% sure. Now you're piquing my interest.
It's like a conveyor belt. So it actually
Get it?
You're not troughing my interest.
Wow, I had.
Okay, so we did have to get to one math problem, which we could probably do in 1 minute, to be honest.
Half a second.
Okay, so let's see if we can do this in half a second. Okay, you got a frequency of 262 hertz. Okay, and you got the speed of sound, which is 343 meters per second, and you're solving for the wavelength. Go.
You divide by 262, I don't know.
So I guess frequency is measured on hertz then.
It's gonna be like
No, it's
Yes, like always.
What do you mean like this? The first time I've encountered this.
Is that true?
No.
First time you've encountered
No.
frequency is hertz?
No.
Let me point down in your notes where it came before. Gross.
Look at the box.
Dab on him.
zing.
Inverse second.
Oh! Warm your hands by the fire.
It's okay. It's okay. He only looks at it right before the test.
Oh, right before, yes, I walk into class, I'm like, better study.